We're literally surrounded by electricity every single day, but have you ever really stopped to think about where almost all of it comes from? It's not really about batteries or solar panels. Nope. It's all about this subtle, totally invisible bridge between two of nature's biggest forces. A discovery that, and I'm not exaggerating, built the modern world as we know it. So let's kick things off with a little puzzle. I want you to imagine you're in a lab, and your job is to create an electric current. Simple enough. But here's the catch. You don't have a battery, you can't plug anything in, you've got nothing that even looks like a power source. Sounds pretty impossible, doesn't it? All you've got are these two items, a simple coil of copper wire, and that wire is hooked up to a little meter that can detect a current. And you've got a plain old bar magnet. That's it. Now, if you just let them sit there, absolutely nothing happens. But watch this. The second you push the magnet into the coil, whoa, see that? The needle jumps. You just made a current out of thin air. Now pull the magnet back out, and it jumps again, just in the other direction. And that leads us to the exact question that completely stumped the first people who saw this, and it's probably what you're wondering right now. If there's no battery, no secret power pack, where in the world is this electricity coming from? Well, the answer comes down to one incredible scientist and one truly revolutionary idea. Okay, let's wind the clock back to 1831. There's this brilliant, self-taught scientist named Michael Faraday, and he is wrestling with this exact problem. He just knew there had to be a link between magnetism and electricity, but he couldn't quite put his finger on it. But after years of trying, he finally cracked the code. And here it is. This is the key to the whole thing. What Faraday finally realized was that just having a magnet hanging out next to a wire wasn't enough. The secret ingredient was movement. It was the change in the magnetic field that the coil was experiencing that actually created the current. Stillness does nothing. Change creates electricity. So let's really break that down. On the left, you've got your stationary magnet. It's creating a magnetic field for sure, but that field isn't changing. And the result? Nothing. No current. But on the right, as that magnet moves, the field that the coil feels is constantly changing. It's getting stronger or weaker. And that is what provides the push, the voltage that gets those electrons flowing. It is all about the change. Now, to really get this, we need to be a little more precise. Saying the field changes is great, but scientists needed a way to actually measure this amount of magnetic field that's passing through the coil. And that measurement has a name. It's called magnetic flux. The idea here is actually pretty straightforward. Just picture these invisible magnetic field lines flowing out of the magnet's north pole and into its south pole. Magnetic flux is basically just a way of counting how many of those lines are actually passing through the opening of our copper coil at any given moment. So, if we want to change the flux, how do we do it? Well, you've got a few options. First, you could change the strength of the magnetic field itself. Use a stronger magnet or just move it closer. Second, you could physically change the area of the loop. Or third, and this is a really important one, you could just rotate the coil inside the field. That changes the angle at which the field lines pass through it. Mess with any of those three things, and you're changing the flux. And here's the beautiful, simple math that wraps all of that up. Flux, which gets the Greek letter phi, is simply the magnetic field strength B times the area of the loop A times something called the cosine of the angle between them, theta. It's an elegant little recipe for a world-changing effect. And all of this leads us right to Faraday's first law of electromagnetic induction. It makes it official. It says that any time the magnetic flux going through a circuit changes, an electromotive force, or EMF, which is really just a fancy word for voltage, gets induced. And of course, if you've got voltage in a circuit, you get a current. But okay, how much voltage do you get? That's where Faraday's second law comes in. It says the amount of voltage you get depends on how fast you change the flux. So if you push the magnet in slowly, you get a little flick on the meter, a little voltage. But if you shove it in there really fast, you get a much bigger jolt of voltage. It's all about the rate of change. But hang on a second. Look closely at that equation. What is that little negative sign doing there? That minus sign is no accident. It's not a typo. It actually represents a really deep and fascinating law of nature. And it took another brilliant scientist to figure out what it was trying to tell us. To get that answer, we have to meet Heinrich Lenz. He's the guy who cracked the case of the mysterious negative sign, and in doing so, he uncovered something fundamental about how the universe seems to respond to change. So here's the core idea.
Nature, it turns out, really doesn't like sudden changes. It's all about the conservation of energy, right? You can't get something for nothing. Lenz's law says that the current you create will always flow in a direction that generates its own magnetic field, and that new field will fight back against the very change that created it in the first place. It's like nature is always pushing back.
Let's walk through it. Step 1, you push the north pole of your magnet toward the coil. That increases the magnetic flux going through it. Step 2, a current gets induced in the wire. And now here comes the magic of Lenz's law in step 3. That new current immediately turns the coil into its own little electromagnet, and it creates a north pole on the side facing the magnet, literally pushing back against it. It opposes the change. And if you tried to pull the magnet away, the coil would flip its poles and try to pull it back in. So cool. Now, this idea of opposition might seem like a tiny detail, but it's part of a much bigger story. Because this entire phenomenon, this thing discovered in a quiet lab with a magnet and a coil, well, it's the single most important principle behind how we generate power on a global scale. A giant power generator is really just our little lab experiment, but on steroids. Instead of pushing a magnet back and forth, you take a massive coil of wire and spin it inside a powerful magnetic field. As it spins, that angle, our friend theta, is constantly changing. And that means the magnetic flux is continuously changing, which produces a continuous, alternating current. And once you know this, you see it everywhere. The water rushing through a hydroelectric dam, all it's doing is spinning a turbine to change magnetic flux. The huge blades of a wind turbine, same deal. Even that tiny little dynamo on a bicycle that powers the headlight, it's all working on this exact same principle. It is literally all around us. In fact, get this, more than 99% of all the electricity generated on planet Earth comes from this one single principle. The simple idea of changing a magnetic field to create a current. When you really stop and let that sink in, it's just staggering. Which brings us right back to where we started. Electromagnetic induction is that invisible bridge. It's the fundamental connection that lets us turn motion, the kinetic energy of spinning turbines, into the electrical energy that powers our entire civilization. So the next time you flip a light switch, just take a second and remember that humble setup in Faraday's lab. A coil of wire, a simple magnet, and the incredible realization that a little bit of change could create energy. It started as just a curious flicker of a needle, and it became the engine of the modern world. It really makes you wonder, doesn't it? As we're out there searching for new ways to power our future, trying to understand the universe better. What other simple, profound connections, what other invisible bridges are just waiting out there to be discovered?